Hello and welcome back to this video series about the Intermediate Math League of Eastern Massachusetts. Today we're going to be finishing up the number theory section from Mate 3. We're going to be talking a little bit more about bases building on what we learned in the last lesson. So let's get into it. Now, just as a side note before I start on bases above 10, I just want to let you know that you will have to have watched my previous lesson or have a lot of knowledge about converting different bases, especially under 10, in order to understand what I'm doing in this lesson, because this lesson will completely build off the last video. So if you haven't seen that, then I recommend watching it before continuing on with this lesson. So first we're going to be talking about bases above 10. Now we already learned how bases work and what bases are, right? I taught you two different concepts to explain what's different in different bases. Now these same concepts apply in bases above 10, but it's a little more complicated to understand because they involve numbers that we've never seen before. So the first concept with the place values is actually pretty similar. So when you have a number in a base above 10, for an example, I have this number 392 in base 12, the place values are represented by the base number 12 to the power of 0, 1, 2, and so on. And if I had a decimal point here, then this number here would be to the -1, and then -2, and -3, and so on. So this concept is really similar, actually, in bases above 10 and bases below 10. And it's actually the exact same, right? You still have the base number to the power of some number based off the place value, which would make this the 144's place. This would be the 12's place, and this would be the 1's place. Now, the next concept about the other way that we learned what bases are in terms of counting is actually quite different. And here's how it works. So if I were to try and count in base 11, it would go like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, 10, 11, 12, 13, 14. And eventually I get to 98, and I'd go 98, 99, 9A, A0, A1, A2. And when I get to AA, I go to 100. So that was probably a bit confusing, but let me explain why this happens. So remember, in any base, the base number is equal to the amount of single-digit numbers there are in that base. So in base 10, we have 10 single-digit numbers, which are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. That's 10 of them total. In base 5, for example, we would have 5 single-digit numbers, so we'd only have 0, 1, 2, 3, and 4. So in base 11, therefore, we should have 11 single-digit numbers. Now, if we count up, we count 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Well, that's only 10. So we have to have another single-digit number that comes after that. And since in base 10, that number doesn't exist, we create a new number, which we call A, to represent that single-digit number. So right here, after 9 comes A. And what this technically represents is the value of 10 in base 10. It's equal to the value of 10, but it's a single digit number. And then you have 10, 11, 12, 13, 14. And when you get to 99, the reason you go to 9A is because if you think about how you count in base 10, say you got to 88. After that, you go to 89 because 9 is the next highest, or is the next single digit number. So you do 88, 89. So therefore, if you're counting in base 11, when you get to 99, instead of going straight to 100, or even instead of going straight to A0, you go to 9A, because A represents the next single digit number. And then after 9A, you go to A0, because say you're starting a new tens, right? Say you're counting by tens, you go 10, 20, 30, and all of these tens are all of these numbers that are multiples of tens start with a single digit number, which are 1, 2, and 3, and they end with a 0. So when you start counting in the tens, you start with 1, 0. When you start counting in the 40s, you start with 4, 0. You don't start with 45 or 42. So therefore, when you start counting in the A's, because A is your next single digit number, you start with A0. And then you count up normally, so you go A1, A2, A3, A4, A5, A6, A7, A8, A9. And before you can go to 100, you have to go to AA, because after 9 comes A. And then after AA, you go to 100. Now, in different bases above 10, say we're counting in base 12, if you're counting the single digit numbers, it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, A and B. In base 15, you would have A, B, C, D, and E. And this is how that works. For every number above 10, you just assign the next letter or the first letter in the alphabet that hasn't been used already, which is why we start with A. And then to represent 11 in a single digit number, we'd have B. To represent 12 in a single digit number, we'd have C, and so on. So counting in bases above 10 is actually a little bit more difficult, but once you understand this concept, it'll be a lot easier to use bases above 10 to convert back and forth between them. All right, so next we need to talk about converting with bases above 10. So converting with bases above 10 is actually pretty similar to converting with bases below 10. You just have to make sure you understand the concepts of how letters work in these conversions. So converting to base 10 is actually pretty similar. You still use the place values, but you have to remember what each letter represents if you have them in a place value. So A would represent the value of 10, B would represent the value of 11, C would represent the value of 12, and so on. So let me show you an example. If I were converting this number to BA and base 12 to base 10, then first I need to label the place values like I would in any other conversion problem to base 10. So I write out my number to BA and I label what place values are here. So this is the 12 to the zeros place, which equals 1. So this is the ones place. Where B is, it's in the 12 to the ones place, or 12's place, because 12 to the 1 is equal to 12. And the 2 is in the 12 to the power of 2's place. And 12 to the power of 2 is 144. So the 2 is in the 144th place. All right, so now that I have my place values labeled, I go about the same process that I normally would, except just remember what these letters represent. So we're going to start with the 2, because this is the most simple one. The 2 is in the 144th place, so it represents that I have two 144s. So in my equation, to find the value of the number in base 10, I write 2 times 144, and then plus what I have in the next place value. So in the next place value, I have the letter B. Now remember, B is a single digit number in base 12. And what it represents is the value of 11, except it's only a single digit number. So if I know that B represents 11, right, because B represents 11 in base 12 as a single digit number, this means that I have 11 12s in the 12s place, because this is the 12s place and B represents 11. So I have 11 12s total in this number. So plus 11 times 12. And then plus whatever I have in this place value. So in this place value, in the ones place, I have A. Now in base 12, A is a single digit number, but it represents the value of 10 in base 10, right? Because in base 12, we can express the value of 10 as a single digit number. So A represents 10. So when we're converting to base 10 then, we see that A represents 10 this place value times whatever the place value is. So plus 10 times 1, because A represents that we have 10 ones when it's in the ones place. So now I have my equation written out in order to find the value of this number in base 10. So 2 times 144 is 288. 11 times 12 is 132. And then plus 10 times 1, which is just 10. And when you simplify this all out, it converts to 430. Oops, I wrote a 2, but 430 in base 10. All right, so next we're going to talk about converting from base 10. So converting from base 10 is a little bit more difficult, but it still follows the same concept. As long as you know what the numbers represent in base 10 and what letters they're going to be converted to in bases above 10, you can still do the exact same thing. So here I have an example. We have 155 in base 10, and we need to convert this to base 13. So the way we do this is we go about it normally. So first we need to list out our powers of 13. So 13 to the power of 0 is 1. 13 to the power of 1 is 13. And then 13 to the power of 2 is 169. And we can stop here because 169 is greater than 155. So we know that 155 is only going to be divisible by 13 and 1. So now we need to see how many times does 13 go into 155. All right, so 155 is divisible by 13 11 times. Because if we multiply 13 by 11, and I'll do this out, 3 times 1 is 3, 1 times 1 is 1. Oops, I don't have that much room. I had a 0, and then 3 times 1 is 3, 1 times 1 is 1, and then we do 13 plus 130, that gives us 143. So 13 times 11 is 143. 13 times 12 would give us 156. So we know that it's 11 times that 13 goes into 155. So we'll do what we do normally. We subtract 13 times 11, and then that equals 155 minus 143, which is 12. So we have 12 remaining. All right, so now we've encountered a problem that we normally wouldn't have if we were converting from a base below 10, or converting to a base below 10, right? But we're converting to base 13, and 13, which is 13 to the power of 1, went into 155 11 times. So that means that when we're writing our first digit in the 13th place of our number in base 13, instead of writing the number 11, because that number can be represented by a single digit number in base 13, we write the letter B, because B represents the value of 11 in a single digit number. So now we have B in the 13th place. All right, so now that we have 12 remaining, we move to our next highest power of 13, which is just 1. And remember, after this, we can stop if we have 0 as a remainder. So we move to 1 and see how many times does 1 go into 12. Well, that one's pretty simple. It goes into 12 12 times, because 1 times 12 is 12. So since it goes into 12 times, then we need to put a 12 in our number in base 13. But remember, 12 can be represented by a single digit number in base 13. And that single digit number, or in this case, letter, is C, right? C represents the value of 12 in a single digit number in base 13. So since 1 goes into 12 times, in the ones place, we're going to put the letter C. And then since we have 0 as a remainder here, or 0 remaining, and we've gotten to the ones place when converting, that means we're all finished. So 155 in base 10 would be equal to BC in base 13. All right, so now I have a review question about converting with bases above 10. If you'd like to try it, I'll give you a few seconds to pause the video, and then I'll explain the answer. So the correct answer to this question is 5A3. So let's convert 718 in base 10 to base 11. So remember, anytime you convert from base 10 into another base, you need to find that base you're converting into, which is base 11 in this case, and list out your powers of that number until they're higher than whatever your base number is, or whatever your number in base 10 is. So let's list out powers of 11. So first we have 1, which is 11 to the power of 0. Then we have 11, which is 11 to the power of 1. Then we have 121, which is 11 squared. And then after 11 squared, I actually don't know this one off the top of my head. So I'm going to do a little bit of quick multiplication to find the answer. So I put a 1 here, a 2 here, a 1 here, and I add these. Oh, 1,331, which is 11 to the power of 3. All right, so now that we have our first 4 powers of 11 listed out, we can stop here because 1,331 is greater than 718. So we know 718 is going to be divisible by only 121, 11, and 1. So now let's go ahead and figure out what values need to go in each place. So 718 first we need to divide by 121. Well, how many times does 121 go into 718? So the answer to that is 5 times, because if we multiply 121 by 5, we get 605. And if we add 121 to 605, it's greater than 718. So 121 goes into 718 5 times. So if we do 718 minus 605, or instead of 605, I should write minus 121 times 5, then that's going to be equal to, and I actually have to do this one out again. So 718 minus 121 times 5, which is 605. 8 minus 5 is 3, 1 minus 0 is 1, and 7 minus 6 is 1. So 113. And now, since 121 went into 718 5 times. In the 121's place in our base 11 number, we write a 5. All right, so now we have 113 remaining, and we move to our next highest power of 11, which we haven't used, which is 11, or 11 to the power of 1. So how many times does 11 go into 113? Well, this one's a little bit more simple than the last one. It goes into it 10 times, because 11 times 10 is 110. So if we subtract 110 from 113, or 11 times 10, then that gives us 3. And since 11 goes into 113 10 times, then we need to put 10 as our next value in our base 11 number. But the number 10 can be represented by a letter in base 11. Because remember, when we're counting up, we get to 7, then we go 8, then we go 9, and then in base 11, we'll have the letter A, which represents the value of 10 except in a single digit number. So therefore, instead of writing 10 here, because we can't, because we're only allowed to write one digit, we have to write the letter A. So it's 5A, and then we still have 3 remaining, and we haven't gone to our ones place yet. All right, so now how many times does our next highest power of 11, which is 1, go into 3? All right, well, 1 goes into 3 times, because 1 goes into a number however many number times that number is. So 3 minus 3 times 1, or I should do 1 times 3 to keep formatting the same. 1 times 3 equals 0. And since 1 goes into 3 times, then in our next place value, in our base 11 number, or in the ones place, we write the number 3. So therefore, since we got to 1, since we have 0 as a remainder, we're finished converting it to base 11. So our final number in base 11 is 5A3. All right, so next we need to talk about multiple base operations. So some questions are going to be a complete pain to do, and they're going to ask you something like the following question below. What is 7 in base 8 plus 1, 2 in base 3 plus 1, 0 in base 2 expressed in base 9? So in this question, this is really annoying because we have 4 different bases, base 8, base 3, base 2, and base 9, that we have to do conversions from, to, and operations with. Now, we only know how to convert certain bases to base 10 and how to convert base 10 to certain bases. Now, there are multiple methods, in fact, to actually do questions like this. You can convert from, say, base 2 to base 8 directly, but it's actually pretty difficult. And for the purposes of the questions they're going to give you in IMLEM, what I mean by that is these questions aren't going to show up a lot, and when they do, it's going to be the hardest question by far on the 3 questions. So for the purposes of that, I'm just going to teach you the easiest method to do it. Convert everything to base 10 and then convert back to whatever base you need to answer in. So in this example then, I'd convert 7 in base 8 to base 10, and then add whatever 1, 2 in base 3 is in base 10, and then multiply that by whatever 1, 0 in base 2 is in base 10, and then convert that base 10 number to base 9. Like I said, there are multiple methods to do this, but they're all really complicated. And this is by far the most simple one. And especially if you don't understand the more complicated methods, it's actually going to take you longer. So let's do this question out. So 7 in base 8 converted to base 10 is just 7, because it represents that you have 7 ones in the one place of base 8. So 7 in base 10, which I'm going to put a little 10 here to represent it in base 10, plus 1, 2 in base 3. So 1, 2 converted from base 3 to base 10 represents you have 2 ones, and you have 1, 3. So 3 plus 2 is 5. So you have 5 in base 10. And I'm going through these conversions pretty quickly, just because we already know how to convert, and I just want to show you what I mean. So 1, 0 in base 2 represents you have 0 ones, or 0 here, and you have 1, 2. So that's 2 in base 10. And then expressed in base 9. So first we need to do out these operations. So 5 times 2 is 10, then 7 plus 10 is 17. So this is 17 in base 10. And now we need to convert 17 in base 10 to base 9. All right, so we list out our powers of 9, which are 1, 9, 81. And since 81 doesn't obviously go into 17, we start with 9. 9 goes into 17 one time, so 17 minus 9 times 1 equals 8. And then we have 8 remaining, and 1 goes into 8 times. So 8 minus, oops, that's an equal sign, 8 minus 1 times 8 equals 0. Since we have 0 remaining, since we finished our ones place, we're done, and since it went into it 8 times, then in base 9, this would be 1/8. All right, so finally, I have a review question about multiple base conversions and operations. If you'd like to try it, I'll give you a few seconds to pause the video, and then I'll explain the answer. So the correct answer to this question was 11010.1. All right, so we'll use our standard method when converting from multiple bases into another base that's not 10, and convert everything to base 10 and then convert back. Especially for a question like this where we have a decimal, that's definitely the easiest thing to do. All right, so first we need to convert 10.2 in base 4 to base 10. All right, so let me write out my number, 10.2. So remember, when you're converting to base 10, you use the place values method. So you have to figure out what each place value represents. All right, so this 0 is in the 4 to the power of 0's place, which is equal to 1. So it's in the 1's place. This 1 is in the 4 to the power of 1's place, which is 4. So the 1 is in the 4's place. And we have a decimal here, but remember, we still need to just use our place values with our base number, which is 4 to the power of something. So this is in the 4 to the power of -1's place. Because if you think about how this should go, it's 1, 0, -1. So it's 4 to the power of -1's place. And what that means is 1 divided by 4 to the power of 1. 4 to the power of 1 is 4. And so 1 divided by 4 is 0.25. So this is in the 0.25's place. All right, so now that we have our place values, we can figure out what this represents. So having a 1 in the 4's place represents we have 1, 4. So 1 times 4 plus having a 0 in the 1's place represents we have 0 ones. Okay, we don't need to write that down. And having a 2 in the 0.25's place represents we have 2 0.25's. So plus 2 times 0.25. All right, so now if we convert this number, it's 1 times 4, which is 4, plus 2 times 0.25, which is 0.5. And then 4 plus 0.5 is 4.5 in base 10. And if you're unfamiliar with converting decimals, this is essentially how it works. You just need to realize that decimals have a negative power, which go down as you go down decimal points. And you still need to you need to figure out what that represents, and you'll use the exact same method in order to do that. So this number is 4.5 in base 10. All right, now, that wasn't a good 5. All right, so now we need to convert 3/4 in base 6 to base 10. All right, so I'll erase some of this stuff and then write out our number 3/4, which I'm going to go through a little bit faster this time because we don't have a decimal in it. So 3/4 in base 6. So this is in the 1's place because it's 6 to the power of 0, and that's 1. And this is in the 6's place because 6 to the power of 1 equals 6. All right, so this represents we have 3 6's because there's a 3 in the 6's place, plus, and then we have 4 1's because there's a 4 in the 1's place. So 3 times 6 is 18, 4 times 1 is 4, and then if we add 18 to 4, that's 22. So this represents 22 in base 10. All right, so now we have our numbers all converted to base 10, right? So now we just have to do the operations on them. So add 4.5 to 22, and if we add that, that gives us 26.5. All right, so now that we have this converted to base 10, we need to convert it as a base 2 numeral, right? So basically, what we need to do is figure out all the powers of base 2, or all the powers of 2 that could go into this. So we'll start with 2 to the power of 0, which is 1. Then we have 2 to the power of 1, which is 2, 2 to the 2, which is 4, 2 to the 3, which is 8, and 2 to the 4, which is 16. And then we have 2 to the 5, which is 32. And we can stop at 32 because 32 is bigger than 26.5. So it's not going to be, or 26.5 is not going to be divisible by 32. But you'll already notice a problem with this. No matter what whole numbers here that we divide by, we're still going to be left with the 0.5 at the end because none of these numbers go into 0.5. And we have that number in our base 10 numeral, 26.5. So here's what we need to do. We can't just stop at 1 here. We have to list out a number below 1 or 2 to the power of negative 1. Because remember, 2 to the 1 is, 1 is 2 to the 0, 2 is 2 to the 1. So now we need to list out 2 to the power of negative 1, which will be less than 1. So 2 to the power of negative 1 is 1 divided by 2 to the power of 1. Because this, remember, this is how negatives work. It's 1 divided by, and then whatever your power is to the negative, except not negative. So 2 to the power of negative 5 would be 1 over 2 to the power of 5, just to make sure you get it. So 2 to the power of negative 1 is 1 over 2 to the 1, which is 1 over 2, and that's 0.5. And since you should already realize 0.5 will go into 0.5, we're not going to have a problem if we use this now. All right, so now let's do our conversions. So the highest power of 2 that goes into 26.5 is 16. And 16 goes into 26.5 just one time. So 26.5 minus 1 times 16 equals 10.5. And since it goes into it one time, our base 2 numeral will start with a 1. All right, so now we have 10.5 remaining. So we move to our next highest power of 2. So that is 8, or 2 to the power of 3. So 8 goes into 10.5 one time, right? Because 10.5 minus 8 times 1 is going to leave us with 2.5. All right, so therefore we should put a 1 in the 8th place of our base 2 numeral. All right, so now we have 2.5 remaining, and we need to figure out how many times does the next highest power of 2 go into it. So the next highest power of 2 is 4. So 4 goes into 2.5 0 times, because 4 is greater than 2.5. So minus 0 times 4, and you don't have to write this out, but I'm doing it just for the purposes of demonstration, equals 2.5. And since it goes into it 0 times, we write a 0 in the 4th place. All right, so now we have 2.5 remaining, and we move to our next highest power of 2, which is 2. 2 goes into 2.5 one time, so minus 1 times 2, and that's going to leave us with 0.5. So since it goes into it one time, we put a 1 in the 2's place. Now we have 0.5, and we move to our next highest power of 2, which is 1. And I know this is tedious, but you really have to make sure to include all your powers of 2, even if it goes into it 0 times. So 1 evidently goes into 0.5 0 times because it's less than 1. So 0 times 1 equals 0.5 remaining. And so in the 1's place, we put a 0 because it went into it 0 times. And then we still have 0.5 remaining. So normally, if you had 0 remaining when you reached 2 to the power of 0, or whatever to the power of 0, or basically when you divided by 1, normally if you had 0 remaining, you could stop here. But since we have 0.5 remaining, which is not equal to 0, we have to continue. So now we have our next power of 2, or next highest power of 2, which is 0.5, and 0.5 goes into 0.5 one time. So if I subtract 1, 0.5, or 1 times 0.5, that leaves me with 0. And since it goes into it one time, in the 0.5's place of our base 2 numeral, we put a 1. And so now since we have 0 remaining, we can stop here. As long as you have a power, or you divide it by a power of your base number that's below that base number to the power of 0, you can stop when you have a remainder of 0. But even if we had a decimal remaining, we'd have to continue dividing by different powers of 2, like 0.25, which is 2 to the negative 2, or 0.125, which is 2 to the power of negative 3. And essentially, you have to keep doing this until you either have a repeating decimal or you finish the question. And in this case, since we had 0 as a remainder, we've converted 10.2, or 10.2 in base 4 plus 34 in base 6 to a base 2 numeral, which is 11010.1. All right, just to quickly review what we've learned this lesson. So first we started by talking about bases above 10 and learned that in the 2 ways that we learned bases, the first concept with place values was pretty similar. You still have your base number to the power of something's place. So this would be the 12 to the power of zeros, 12 to the power of 1s, and 12 to the power of 2's place in base 12. And that doesn't really change. But we also learned that the second concept is a little bit more difficult to grasp, because in bases above 10, you have above 10 or more than 10 single digit numbers. So since those single digit numbers don't exist in base 10, which we normally operate in, we assign a letter to them. So in base 11, the value of 10 in a single digit number, or the single digit number which comes after 9, would be represented by A. And then in higher bases, the next one would be B and C and D and so forth. Then we talked about converting with bases above 10. So you just have to remember when converting from or to base 10 with bases above 10, that these letters, A represents 10, B represents 11, and C represents 12, and so on, except in a single digit number. So we converted 2BA from base 12 to base 10 by realizing that B represented we had 11 12s, and A represented we had 10 11 or 10 ones, because we had a B in the 12th place and A in the 1's place. And then we converted 155 in base 10 to base 13, which left us, if I can remember correctly, with a value of BA, because we had a B in the 13's place and an A in the 1's place, because 13 goes into 155 11 times, and 1 goes into the remainder of that 10 times. Then we converted 718 in base 10 to base 11, which gave us 5A3. After that, we talked about multiple base operations, and I let you know that there are multiple methods to do this, but since they're all pretty complicated, and since the one that I taught you is really easy, you should just convert everything to base 10 and then convert it to your final base, because that will make it a heck of a lot easier. And especially if you don't understand how those other methods work, then it's actually going to save you time to do this. And then finally, we did a review question where we added 10.2 in base 4 and 34 in base 6, and expressed that as a base 2 numeral, which gave us 11010.1. All right, so that's all I have for you today, and this is actually the last video in Number Theory Meet 3. Number Theory Meet 3 is really difficult because bases are really difficult, but I really hope this video helped. See you next time.